Okay, hey, what's up, everybody? This is Dr. Tracy Tooth from EE135. This is going to be the third part of the fuel cell series. So today we're going to talk about molten carbonate fuel cells, right? So molten and carbon fuel cells, just like any other fuel cells, take in the oxygen, take in the hydrogen, and then emits energy in water, right? The only difference between this fuel cell and others is this electrolyte inside. What is it made out of, and what type of ions it pushes through. So this one is going to push through arc carbonate ions. So first, it's made of lithium carbonate and potassium carbonate, right? So this is material with the electrolyte. Given high temps, and at high temps, I think it's 600 degrees Celsius, 600 to 650 degrees Celsius, it will melt. So the lithium carbonate and potassium carbonate will actually melt into kind of a liquid, and will pass carbon ion, right? It passes. That's this CO3, right? So the idea here is the carbonate ion, which is CO3 2 minus, right? So it's 3 oxygen molecules, and the 2 minus is the electrons difference. So we're gonna subscript that. This is gonna be superscript. If I'll be accurate, this should be directly on top here, but we can't really do that right now unless we use equation editor. So we're just gonna deal with that. So the idea here is that I goofed it. So the idea here is that this carbonate ion, this is going to go through electrolyte, right? And that's what's going to force these electrons through. So just like before, what we're going to do is we're going to go through and look at the chemical equation on the anode and the cathode and see what happens. So let's look at the anode first. Obviously, the most important thing we put in is going to be the fuel, right? 2 hydrogen 2, right? So we're going to put 4 hydrogen molecules that are going to come in. This will then go with us and engage with the carbonate ions. So in this case here, you look over here, you get 2CO. Well, I'm just going to copy up here. 2CO3, right? That will then have a chemical equation. Let me superscript off. This will then turn into, oh man. So this will then combine over and give us the electrons that we need. And the water and some other stuff coming out. So first off, let's see the 4 electrons. So it's going to 4 electrons going to come out, right? So 4E minus. Again, remember, this is the 4 electrons that are going to come out the negative terminal, go through the load, release this energy, and go into positive terminals. Right? The whole idea is this electron is going to want to get away from this anode because there's too many electrons here, go through the load, because that's an easier path than going through the carbonate ion, through the electrolyte. Because the electrolyte will not actually let the electrons through. It's kind of like a barrier. And on the other side, all the electrons will combine with the oxygen and carbon monoxide coming in and create this carbonate ion. So this is kind of the loop that happens. So we're going to have that part, the electrons, and then what else gets combined. So we're going to have 4 hydrogen molecules and 2 carbon molecules and 6 oxygen molecules, right? So here, 4 hydrogen and 2 of the 6 oxygen combine to water. And then the rest are going to combine to have 2 CO and 4 oxygen. So we're going to have 2 CO and then 4 into 2, which is 2. So we're going to have 2 coming out. So here, this is going to be our water molecules. And this over here, you've seen this before, this is our carbon dioxide. So you can see for this equation, let's get some spaces in here to make it look neater. Here we got 2 hydrogen and the carbon ions combine in an anode and get 4 electrons, 2 water molecules, and 2 carbon dioxide molecules, right? So that is for the anode side. Then let's see what happens on the cathode side, right? On the cathode side here, let's undo this subscript stuff. Boom, boom. Here we're going to have oxygen come in. Plus, we're going to have our carbon dioxide. We need a carbon dioxide to combine with the oxygen to create the carbonate ions in the first place. Conveniently here, the carbon dioxide coming out of the anode can be cycled back into the cathode. Right? So we're going to have the same amount come in. So here you can see in a perfect environment, the carbon dioxide that comes in is going to go through, come out of the fuel cell, will go all the way back into the fuel cell. So then we won't actually be emitting anything into the atmosphere, right? So here, our cathode side, we got the oxygen, we got the 2 carbon dioxide molecules, and what happens is this is going to split up and have our 2 carbonate ions, right? So pretty much this carbonate ions here is going to be the resultant. I copied the wrong thing. This should be the carbon monoxide. There we go. So oxygen and carbon dioxide come in, not monoxide, dioxide, and then the output is going to be the carbonate ions, like this. And we got to think of the electrons, right? To balance those equations, we had 4 electrons come in. So here we got to add in right here plus, oh, get rid of subscript, 4 electrons, and I killed the plus sign. There we go. So here, the 4 electrons will get pulled into this chemical reaction to create this carbonate ions. And this part right here, just combining, this is what pulls electrons through the terminal, and that creates our load and our energy. So overall, so here in a perfect, again, let's get rid of subscript BS. Oops, what did I do? In a perfect world, the carbon dioxide, or I would say all of the carbon dioxide coming out will be fed back in. So more likely than not, in real life, you're not going to get all of it to have this perfect feedback here, but you can get a really high percentage. And the idea is, if we keep this whole carbon dioxide system enclosed inside the fuel cell, we're not actually emitting any dangerous gases into the environment and harming it, right? So in the end of the day, total, the input to the fuel cell was what? All we really put into a fuel cell was hydrogen and oxygen. Then we get out just water and, of course, energy. That's the whole reason why we're doing this. So here, the hydrogen comes in, oxygen comes out, we get the energy. This is pretty much what fuel cells are, right? As for, let's say, advantages and disadvantages, it's pretty much same as the solid oxide fuel cell, right? Guys still do the whole high temperature thing. The efficiency is pretty high up there. So the only big difference between this one and the other ones is, so it's pretty much the same as the solid oxide fuel, except the internal corrosion that can occur with the carbonate electrolyte, right? Current corrosion of electrolyte. So pretty much any time you deal with carbon dioxide or carbonate ions, as it passes through this electrolyte, it's going to eventually damage it, right? That's what corrosion is. So pretty much for this fuel cell, there's going to be a life cycle. Eventually, that electrolyte is going to be so corroded that it's not going to be able to use it anymore, right? But I guess compared to the solid oxide fuel here, is this temperature range is a big difference, right? Sometimes this 1,000 degrees Celsius is not going to be useful. It's going to be impractical, so then we're going to use this molten carbonate fuel cell instead. Right? So this pretty much sums up all three of the online lectures we did for the fuel cell part. And hopefully you can go back and read this. I'm going to post all this 3-slide PowerPoint online just to show you what I made and have something to study with. So hopefully we'll see you coming Monday. And Monday we're going to talk about a couple more, I think one more fuel cell, and then talk about kind of the comparison and how do we actually use them. Because right now all we're really doing is chemistry. So if you come to school next week, and we'll wrap through this fuel cell, and that's about it. So, last thing, I'm going to post some homework and the quiz for this coming week. Probably have something to do with this stuff and what we're going to do next week. So definitely pay attention to all the information given. All right. So you guys have a good one.